It is evident that these features could also be explained in terms of large water bodies remnant from the flood, alluvial climates persisting after the flood for a time, and continuing intermittent uplift of the lands. Talking about all these features showing something of a lot less water was there way before the land got to where it could be observed today. It may be that the difficulty of unraveling Great Lakes history has been in part due to the neglect of this very factor of the flood. Just put your head in the sand when it comes to the worldwide flood, because it's out of the Bible. It talks about God. We recognize, however, that much evidence exists in favor of the glacial explanation of the lakes, and we see no necessary reason to question it from the biblical point of view. In either case, whether the water came directly from the retreating deluge waters or from only indirectly, from them by way of the great ice sheet to which they contributed, the ice ages and so on, it is clear that in the very recent geologic past, both in glaciated and non-glaciated regions, a much greater part of our present continent was covered by water than at present. So the problem with this is everything points back further. If it's some local glaciated thing, where did all that water come before that? So evidence of a much greater river activity in the past. Point C. Introduction. The rivers of the world universally give evidence of having once carried much larger volumes of water than do their present remnants. Colorado River, Grand Canyon. This is evidenced both by the raised river terraces nearly always found along their courses and by the extensive deposits of alluvium along their flood plains. I think this is 2 words. These terraces are so common that an entire terminology has been developed attempting to categorize them in different types on the basis of their assumed evolution. See, they're going to call the same thing over here something different over there because they can't figure out why it's different. But they can't accept the possibility of a worldwide flood. Change the name just to make it more complicated. Many streams are actually called underfit streams because the valleys they traverse are much too large to have been constructed by them. So they make up something else. If a stream, or more correctly the size of the stream meanders, is too small for the size of the valley, the stream is said to be underfit. If too large, it is referred to as overfit. Wow. It is difficult to cite examples of overfit rivers or streams with floodplains too small for the size of the stream. Hence, there may well be a question whether overfit streams exist. The underfit condition can persist indefinitely. Hence, many examples of such streams exist. But they have no way of explaining how they got there as observed. Well, dry stream channels. Another point. Similarly, take out the italics. Similarly, there are many examples known of former stream channels that are now completely dry. Some of these, of course, have resulted from shifting of channels, but many others were evidently formed by streams that no longer exist, except perhaps in greatly reduced volume as subsurface streams. These are especially common in the glaciated regions and, of course, are usually, but not always accurately attributed to formation by glacial meltwaters. But they are also formed in the non-glaciated regions. And how do you know? Were you there 100 million years ago? Certain sand and gravel deposits indicate former existence of great rivers. In addition, sand and gravel deposits are found in many places that indicate the former existence of great rivers whose valleys now are buried by the later glacial deposits. A notable example of this phenomenon is the so-called Teays River, which once coursed across the continental United States, nearly from the Atlantic to the present Mississippi, where it debouched into a far northerly embayment, a formation of the bay of the old Gulf of Mexico. This was truly a mighty river in every sense of the word. It was this valley that Tite long ago recognized as the abandoned course of a great river. Thick beds of sand and gravel, including water-torn boulders up to 12 inches or more in diameter, lie upon the valley floor. Where did they come from? Many, composed of rocks quite dissimilar to the bedrock of the valley, show unmistakably that they were washed by river action from the bedrock region of the Blue Ridge. Only a great and powerful river could have accomplished this. Raymond E. Jansen. Unanswered questions. They just don't want to consider plausible alternative of the worldwide flood. This great river probably represented a channel developed by the retreating floodwaters in response to the uplifting of the present Appalachian region. With its huge load of sand and gravel and boulders, it could have scoured out its great channel rapidly and also carried an immense amount of alluvial materials, initiate the formation of the Mississippi Delta region. With its great network of tributaries, it helped carve the landscape of a large portion of the continent. The amount of sediment, mud, silt, sand, and pebbles which it eroded and carried to the sea must have been tremendous. The sea into which it poured these sediments was the long, narrow arm of the Gulf of Mexico. This long seaway from southern Illinois to New Orleans has been completely filled, and the great delta now juts far into the Gulf proper. It is evident that the greater bulk of the delta was built by the T's, with the Mississippi adding only the latest portions. Hence, the immense delta more appropriately might be called the delta of the T's. Glacial geologists believe that the continental glaciers then buried the T's and other such streams under a thick deposit of till and completely changed the surface drainage pattern when they retreated. Valleys and rivers evidence much greater river activity in the past. Same thing, wherever we look, we don't have anything to the opposite. Valleys and rivers, wherever you go, too much water. But it is the present valleys and rivers which appear to give the strongest witness to the former existence of much larger rates of river flow than now. Too much water came by in the past to show what we see in the present. Evolutionists von England and Castor denied that there could have been a greater river flow in spite of the evidence. In a stream valley, the width of the channel occupied by the current may be only a small fraction of the width of the valley floor. Furthermore, the banks of the channel are relatively low compared to the height of the valley sides. Grand Canyon, Colorado River. In a word, valleys commonly appear to be far too large to have been formed by the streams that utilize them. Over and over again, the full thought is to infer that the stream was once a much greater current. Oh no, we don't want to do that. This almost always proves to be an unreasonable conclusion because no evidence can be found that a larger volume of drainage was ever available. Why? The evidence is the wider canyon in the Grand Canyon, Colorado versus minutiae. What does water do? It goes down to bedrock and then spreads out. Where's all that water? The water going down the Colorado River now is dwarfed by the size of the canyon surrounding it. O.D. von England. These guys, I don't know how they get there, but, well, I guess if everybody wants to read your material, then they'll be able to author it and sell books. If, as indicated, the reason for rejecting the plain indication of a former much greater stream flow is merely the lack of a source of the required waters, because you can't find them now, we would suggest for consideration once again the waters of the flood, which in response to the uplift of the lands and subsidence of the ocean beds required to be rapidly and powerfully transported to the sea. Furthermore, the rainfall of the early post-Diluvian times must have been much greater in most places than it is now. Point 5. Raised river terrace evidence higher levels and volumes of stream runoff. Similarly, the former higher levels and volumes of stream runoff are shown by the raised river terraces, but in like manner this evidence is commonly and falsely explained away by evolutionists as caused by various complicated processes of geomorphic evolution. They invent stuff and try to reverse engineer all the way back to what they want to see. Most large stream valleys are both deeply filled with alluvium and exhibit well-developed raised terraces more or less paralleling their present slopes. These conditions are, of course, exactly what would be expected on the basis of the biblical descriptions of the tectonically induced retreat of the waters after the flood. Nevertheless, they are commonly and falsely explained by the evolutionists on a strictly uniformitarian basis. Thus, old river terraces are falsely attributed to gradual formation of a floodplain by lateral planation, that is, by the meandering of the river back and forth across its valley, gradually eroding the valley sides and smoothing out the valley floor, contrary to the laws of hydrodynamics of moving bodies of water. Then the evolutionists must insist that rejuvenation of the river somehow takes place, so that it begins a down-cutting action, again violating the laws of hydrodynamics, which demand bottom cutting first, all the way down to bedrock first, before erosion of the river banks sideways, leaving its former floodplain perched above its new level as a raised terrace. It is plain that there is little actual evidence of this extensive lateral corrosion of streams, especially when cutting through the bedrock. Alluvial streams, such as the lower Mississippi, of course, have a wide meander belt, but they are cutting into an alluvial fill and not bedrock, which had already been deposited by earlier flows of greater magnitude, so that the floodplain itself is basically a plane of deposition rather than erosion. If rivers that flow across floodplains many times wider than their meander belts are observed, it will be found that in relatively few places are the streams actually against and undercutting the valley sides. This suggests at least that there may be a limiting width of valley flat beyond which lateral erosion becomes insignificant. The valleys of many, if not most, of the world's large rivers are so deeply filled with alluvium that it may seem inappropriate to consider their floodplains as veneers over bedrock valley flats. The alluvial fills in such valleys as those of the Mississippi, Missouri, and Ohio in places are several 100 feet thick. Go down there, you're going to find bedrock, Thornberry. Thus, the lateral corrosion hypothesis of river terrace formation appears to be mainly a uniformitarian assumption rather than an actual present geomorphic process. The Mississippi and its terraces have been studied properly more than any other stream, and although a complex history has been falsely deduced for it, the evidence strongly refutes the notion that its broad valley could ever have been eroded by later planation. Russell, long a student of the Mississippi Delta geology and now dean of the graduate school at LSU, says, broad floodplains are characteristic of most rivers leading to the sea. For many years, these were explained on an erosional basis. The rivers were pictured as having cut down their valleys to a base level established by the sea, after which their energies were directed toward lateral corrosion, or valley widening. The alluvium of floodplains was thought of as a thin veneer resting on laterally planed bedrock. Within more years, however, the alluvium of many of these floodplains has been penetrated by borings, which in practically all cases reveal valley fill which is many, many times deeper than the deepest pools scoured along the riverbanks. In the case of the lower Mississippi Valley, the character of the bedrock topography which underlies the alluvium is comparatively well known, and it contains river trenches several 100 feet deep, not a few inches, while the river is rarely over 60 feet and in no case as much as 200 feet deep. So how did it get there? Worldwide flood. Then it reversed. The flood cut out this deep canyon and then filled it up with sediment. Richard J. Russell, Instability of Sea Level, American scientist. Okay. That these extensive alluvial deposits, not only in the delta region but also along the continental shelves, required a tremendous river to erode and transport and finally deposit them seems as obvious as anything could well be. By all odds, The most reasonable explanation